current.
So S is equal to EG
times IL.
IL, the line current, yeah.
Yep. And so I've done 650 angle 0.
Yeah.
And then times 16.6 angle minus 47. Because that says in the question that lags the voltage by 47 degrees. And then when you multiply that out,
yeah.
Have I mixed
the
them up?
The thing is, what you've done there, Robbie, okay, is you've got, well,
was it reactive?
you're okay, but you don't need the angle for the power.
Okay.
It is simply the magnitude of the voltage.
Okay.
Times, because remember, you've got 3 different powers you can deal with: S, Q, and P.
Yeah.
Yeah. So if the line current is the actual current flowing in the line, and that's the current that gives you S.
Okay.
Yeah. There is an angle, but at this stage in the calculation, you don't need that.
Okay.
All right.
So if I forget,
doesn't matter, because
if
you put that in the exam, you still get your marks.
Yeah.
So I won't worry about it, because it ain't actually relevant. So you should be doing that times 16.6, and your answer was
10,790 VA.
Yeah, that's what I got as well.
10,790 VA.
Yep.
Yeah. 10.8 kVA. Is what I've moved that to. Yeah.
Yep.
All right, but you'd get full marks if you just left it as 10,790 VA anyway.
Okay.
All right.
Yep.
Mike.
Yes, Lewis.
Will you be sending out the work solutions after this lesson as well?
I will.
Right,
I will. Well, I won't send them out. I'll put them on Brightspace.
Yeah, that's fine. Yeah.
So on Brightspace, what I do is any videos, the handout that I sent anyway, the blank one, if there is a handout, set of solutions, and these whiteboard screens that I'm writing on.
Okay.
All go on there. Yeah. All right. So you can find all the other ones for every other week. The only time is if I might have lost something, like lost a video or something, but I don't think I've done that this year, not on this module.
All right. Great. Yeah, thank you.
Okay, so that's that part. So I'm going, Lewis, how would you tackle the second part, active power? It might help if I kept my triangle up there, because you've got S, you've got 47 degrees in there, ain't you, Robbie? And that's Q. Yeah. And that's always useful to draw the diagram. So you now know S. That's 10,790.
And you have we haven't got Q, have we?
You haven't got Q, not yet, no.
T is adjacent. That's that Socrates stuff, isn't it?
Yeah, it is, yeah.
Hang on. That's cause. Would you use? You got the hypotenuse. You haven't got the adjacent, but you've got the. Would you use?
No, but what we're looking for is we're trying to find the adjacent. We're trying to find P.
Right. So would you use P equals S times cos 47 degrees?
Yes. P equals S cos the angle. Yeah. So that's 10 790 times cosine 47 degrees.
Yeah, and if you also that's always the easiest one for me to remember as well, because the power factor is cos theta.
Yeah.
You'll know that that is P over S. So if you rearrange that, that's how you get that P equals S
Yeah.
times
Yeah.
cos theta.
Yeah.
So I
And
always find
if you notice, one thing to notice is I've used 10790 and not the rounded 10.8 kVA.
yeah.
Yeah, because I'll be doubling up on my rounding then. All right.
Yeah.
And the answer is Warren.
No, I didn't get that. I did it a different way. It seemed to be.
Did you? What did you do?
I don't know, but it looks wrong.
That's 7359, Robbie. Is that what you got?
Yeah, I got
7359.
Yeah, I did mine slightly differently to that.
Just let me know what you've done, Warren.
Yeah, I did IP equals IL multiplied by cos, then the angle, to then find out the current, and then I then did a power equals the line a voltage multiplied by the current, which got me the same answer.
Yeah. Did you get the same answer?
Yeah, I got S7358 watts.
Yeah, that's kind of a strange way to go about it.
Yeah.
But if you got the right answer in the exam, you get all the marks
Okay then.
in that instance, because you're
Yeah, I
not
kinda
being
went the wrong
told
way
to use
round.
any, not being asked to do any particular method, just being
Yeah.
asked to find it. Yeah.
All right.
Okay. So C, reactive power. Q.
Yeah.
How do you do that, Lewis?
Has our calculator got to be in degrees throughout the whole paper, or have we got to swap between them?
There could well be places where you have to go to radians.
Right, okay.
Okay.
So if I leave it in degrees for the majority of it.
I think you might be all right for most of it.
Yeah, okay.
I
I had mine in radians then, I weren't getting that answer. But obviously in the exam, I wouldn't know. Well, I should know, but you know what I mean. You can kind of
if you see
make that mistake
where you might notice here with an angle, Lewis, is if you think you know what 47 degrees look like, don't you?
Yeah.
So if you don't get if you done a calculation and you got 1.23 and you're expecting something around 47 degrees, you should recognize that that's wrong.
Yeah.
Yeah?
Yeah, that's fair enough.
All right. That's the best I can do, really.
Yeah.
I don't think we have radians a lot, but I think there might be somewhere. I'm not absolutely sure. I think most of the time we've been in degrees on this module.
Yeah.
But I can't promise there won't be any radians.
No, that's okay. I'm going to leave it in degrees anyway.
Yeah. Basically, if you see omega and pi, you need involved with angles. You need to go radians.
Yeah.
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 All right.
Mhm.
Yeah, I did notice on the formula sheet we have got the equation for a sine wave, but I haven't actually found that any of the tutorial questions, because I've been through them all again this weekend. I've not found a single question where it requires
that's involved in. Yeah.
Yeah.
Yeah. Yeah. Okay. Right. Anyway, reactive power, because we now know two sides of our triangle. So how can we find the third side?
Q equals the square root of S squared minus P squared.
S squared minus P squared.
Yeah. Oh,
So that's the square root of 10790 squared minus 7359 squared.
Yeah, so for that I got 7891 var.
7891 var. That's what I got.
Mm-hmm.
Yep.
Yep.
Okay. So,
I know.
moving on from that, we now got a situation where the question is saying a D. So this is our situation we're currently in, where S was 10,790, yeah. Q was 7,359, and P was no, Q is 7,891. And P was 7,359. How are we going to tackle this issue? It says the new apparent power and phase angle, because this is currently 47 degrees. The new apparent power and phase angle if a capacitor is fitted that provides reactive power to reduce the overall Q to 1500 VAR. So we're talking about adding a capacitor so that this angle comes down such that Q new equals 1500 VAR. And like I always say, it's worthwhile putting a sketch. So we want to know this new angle as well. So we find the new apparent power, S new, if Q new is 1500. Always remembering what happens with P under that kind of situation.
Always remains the same.
Remains the same. Yeah. Okay. So how can we find, this is D, S new.
So what I've done for that one is I've done S new is equal to the square root of P squared plus Q new squared.
Yeah.
And so I didn't bother to draw a new triangle though, but I suppose that would probably pick us marks up in the exam, wouldn't it?
You're not asked for it.
Yeah.
In some cases you might be.
Yeah.
But I think it helps to show your understanding. If you've gone wrong, there might be some credit in that for a mark or two.
Yeah.
It's always worthwhile to just do one, and that helps you visualize what you're trying to calculate. Or I think anyway.
Yeah. Okay.
So we're talking about 7,359 squared plus 1,500 squared.
Yeah.
Yeah.
Yep.
And that comes out at.
I got 7510 VA.
7510 VA. Yeah.
Mm-hmm.
And the new angle.
So I then done the new power factor would be P over S new.
Yeah.
Which would then be 7,359 over 7,510, which gave me 0.98.
Yeah.
And I then done as the power factor equals cos theta, then theta would be cos to the -1 of 0.98, which then gave me 11.5 degrees.
Yeah. Yeah. And I was starting to wonder then, because on my answer I'd done cos to the -1 of that, so I didn't resolve that to 0.98. But you got exactly the same answer as me.
Yeah,
I got 11.5.
You do it in one step rather than two, then, wouldn't you?
Yeah. Well, there's a chance that when you go to this power factor here, cos theta 0.98, that you round it again, and then you're rounding it again down here with the angle. But it hasn't made any difference. So
no. The thing I would like to check as well is I always like to see what the power factor is, because I did write one and I got over 1, and I think I didn't notice until I got to the end.
Can't do that.
So,
that's not possible.
Yeah, so I think when you see it's 0.98, you go, okay, that's about right.
Yeah.
But yeah, no, I think your way is probably a bit quicker. So.
Okay.
Yep.
Yeah. Right, so that's question 1. So there's 10 marks for doing that. Not too difficult.
How many marks is a paper? 100 marks.
100 marks the paper. 4 shorter questions, 10 marks each, and 2 longer questions, 30 marks each.
Okay.
All right.
Yeah.
So what we go now is move on to question 2. Hang on a minute, guys. Hang on. No. Right, boys. In the inductor of inductance 35 millihenries and resistance 16 ohms. So again, that's not asking you for a circuit, but that's often worthwhile drawing one. Inductor has a inductance and resistance 35 millihenries, 16 ohms, connected in parallel with a further resistive load of 34 ohms. Connected to a 110 volt supply at 50 hertz. Calculate the reactance of the inductor, the total impedance of the circuit in polar form, and the total current flowing in polar form, and the power factor of the circuit. So there's question 2. How would you go about doing I, Warren?
No, I can't find it.
Did you do this question or?
No, I think I skipped this one.
Oh, okay. Lewis, do you know? So we're looking at finding XL.
Oh, I can't remember what the formula is. The XL equals.
It's an XC. Oh.
What's that formula? Robbie, help me out here. XL equals what? What's that formula?
2 pi FL.
2 pi FL.
2 pi FL. Yeah.
Yeah.
So it's 2 pi times 50.
Yeah.
Times 35 times 10 to the minus 3.
Yeah.
Equals 11 ohms.
Yep, that's what I've got.
Let me just put it in my calculator just for sounding purposes. Yeah, I got that.
All right.
Yeah.
Right, B, total impedance.
Corona. Yeah,
Robbie, where you go? What you done?
I'm not sure if I went right on this one or not, but what I've done is I've done, obviously I've worked out the impedance of the inductor, which I've called ZL.
Yeah.
And I've just done the 16 ohms plus 11J ohms is how I've worked that out.
Yeah. Okay. The solution I've got in the solutions, I've used the product over sum formula.
Okay.
So ZT is ZR times ZL, which you say you're separately calculated.
Yeah, I think I've messed up.
Yeah.
Here. Just add them together.
You've added no. Well, you're not wrong in adding them together, because on the bottom they need to be added together.
Okay.
Yeah.
Yeah. Okay.
So that's worthwhile me going through this method, because what you've done is you've done ZR plus ZL, yeah, and calculated a total for those two, and then you've paralleled it up with the other ZR.
No, all I done was I done ZT equals ZL plus ZR, and I left it at that. So obviously I've only done part of the.
Yeah, so you've only done the series bit here.
Yeah.
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 And anyway, even in my notation, I've not been consistent, because we need to call these the top line has got to go ZRL, because that's the resistance of the inductor.
Mm-hmm.
ZL, the reactance of the inductor. Tell you what, let's do this a bit different. RL, this is where you can get hung up in notation. XL over RL plus XL No, I'm still doing it wrong, aren't I? We call this, let's draw this as R, that's RL, and that's XL. Yep.
Yeah.
So product over sum is I've got a horrible feeling maybe even my solution isn't right. R times RL plus XL over R plus RL plus XL. Yeah.
Where did you get that formula from?
Well, as product over sum. So when you've got a parallel circuit, just a parallel circuit of two resistors, yeah, you can find RT from R1 times R2 over R1 plus R2.
Yeah.
Would you be happier if we went down Robbie's route for solving this question? Yeah, where you do things separately. So we find, I think that might be better.
I think it's going to be a little bit easier to understand because
right. So what you done, Robbie? I'm guessing now you found ZL. Yeah.
No, I think I've messed up a bit here because what I've
We'll go down this.
Yeah, so
we'll go down this route anyway.
I started finding ZL, so I've done 16 plus 11J ohms.
That's that anyway. R plus XL, yeah?
Yeah.
Which is 16 plus 11J.
Plus 11J ohms, yeah.
Yeah?
Yeah. And then to find ZT, all I've done is I've added ZL, and then what I've called ZR, which is just a resistor. So obviously I've not done.
No, you have to do. You've got to do the. At some point, you've got to do the product over sum.
Yeah.
Yeah.
Yeah. So I suppose if I was to do this again, I would convert probably ZL to polar form.
Yeah. Well, we need to do that.
So yeah.
So now
So
once
let's
we've got
convert.
that, do we then just do ZT equals R times ZL over R plus ZL?
Yes.
Right. Okay, that makes more sense.
Yeah. So if we convert that ZL to polar.
Yep. So I've got 19.4.
19.4 ohms. Angle
34.5.
Yep.
Yep.
So that's ZL. Now
Yeah.
we need to do ZT is R times ZL over R plus ZL. Yep.
Yeah.
Yeah.
So that is, what's the other resistor?
34.
34. So it's 34 times 19.4 angle 34.5.
Do we not have to put an angle for the resistor?
Yeah, but the angle for the resistor is 0, Lewis.
Yeah.
Always is.
Yeah. Yeah.
Alright.
You won't get penalised for putting that in, just so it looks better in my head.
No. If you feel happier putting it in, then put it in.
Yeah.
I usually leave it out in this case, but by all means put it in. You'll not lose anything for putting it in, as long as you get it right. As long as you put 0. All right, and then down the bottom, we're going to have 34 plus, because we're going to add them together. We're going to use the rectangular form on the bottom. Yeah.
Mm-hmm.
So now we need to resolve the top. So we've got to do 34 times 19.4.
So I've got, on the top, I've ended up with 659.6.
660.
Yep.
Angle 34.5 degrees. And then down the bottom, we've got 34 and 16 is 50. Yeah. Plus 11J, which we can then convert that bottom one. So keep the top polar. And now we convert the bottom to polar.
Yeah, so for the bottom in polar, I got 51.2.
Yeah. Angle
12.4
degrees. I better make that look like a degrees and not a 0, won't I? Yeah.
Yep.
With a final answer of 12.9.
Yeah, 12.9
ohms. Angle 22.1.
Yeah.
Yeah. My solution is correct. That's just that I've done it in one go, so I haven't separately calculated ZL to start with. Just done it all in one go.
Yeah.
All right.
1, 2. Yeah.
So that's that bit. All right with that, Warren?
Yep, just writing everything down.
Right, can I move on, Warren? You got it all?
Yeah, I'm all good.
Right. So, Warren, current.
What are we on, number?
I is equal to
See.
just go to show how even the best can slip up. I've got I is equal to E over I on the solutions.
I got the power.
So that's just Ohm's law, Warren, isn't it?
Yeah, I'll just put I because.
E over ZT.
P
Yeah.
equals I. Yeah.
110 supply voltage over 12.9 angle 22.1 equals 8.53, Robbie?
Yeah, I was around at 12.5. I'll put a 3 after it. There you go.
Angle
3. Angle
minus 22.1 degrees. Yep.
Mm-hmm.
D, power factor.
So for this one, I've written, because I believe the angle for the current is the same as the power, is it? Is that correct?
Yeah. Yeah, that's yeah.
I've put as power is in phase with current, theta is equal to minus 22.1. So therefore the power factor, cos theta, is equal to cos of minus 22.1.
Yeah. You can actually drop the minus there because the power factor is just what the cosine of the angle, the magnitude of the angle is.
Okay.
Did he get 0.932 anyway?
Yeah, well, I got 0.926. So
yeah.
Let me just take the minus off, see if it make any difference. Yeah, 0.926.
Yeah. I done is equal to cosine of 22.1 degrees. And I got 0.932, but maybe I put the wrong number in. That was a long while ago I wrote these questions.
Yeah.
That is 0.926 or 927 actually.
Yeah.
Oh yeah, if you round it, yeah. Didn't notice that 5 there.
All right.
Yep.
So there's another easy 10 marks. You're halfway to passing.
Whee.
All right. Question 3.
I'm just trying to write down the last bit.
Oh, sorry, Lewis.
Right. 2.127. Yeah, okay, perfect. Finger.
Yep. All right.
Yeah.
Mm-hmm.
So, 3-phase balanced star.
So just a quick
And neutral.
question before we start this one. In
Yep.
terms of the power formulas and the line and phase voltage and line and phase current, is that something we're going to get, or is that something we need to remember?
If you want an honest answer, I can't remember.
Okay, no worries. Yeah,
I'll take a look at the paper in a minute and just refresh my memory as to what. From memory, there is not much on the formula sheet because not a lot of it's needed.
Yeah, because I kept messing up where my, like, say with the RMS voltage and stuff, where the root 2 was and where the root 3 was, and yeah. But yeah, if I need to remember them, I'll just try and practice them a bit more. But
well, RMS's involves root 2.
yeah.
Line and phase voltage and currents involves root 3.
Yeah.
The way I remember line and phase is that, well, in delta, sorry, in star, your line voltage between two lines, 400 volts on our mains, is bigger than your phase voltage. So you must divide the line voltage by root 3 to make the phase voltage smaller.
Okay, right.
Yeah?
Yeah.
And then in delta, your phase currents, because they go into your line currents split into two currents, so it's the currents that must be smaller. So you divide the line current by root 3 to get the smaller phase current. And if you can remember just one way round, then you can just rearrange the formula for the other way round.
Yeah.
Yeah.
Yeah. Okay.
But I will take a look at the actual paper and see, get an idea of what's on it.
Okay.
Yeah, go on, Lewis.
I think Ben's trying to get in the call or something. He said, "Can you accept him?"
Roger's there.
Ben said that he's trying to get in or something.
I can't see Ben. He's not in the participants list. Waiting.
Is he using the right Zoom code?
Hang on.
It changed into.
I'll turn the waiting room off for a start. Well, he's been with us since we done the code.
Yeah.
Since that changed.
He said he hasn't got that code, but he must have because he's been in here quite a few times, hasn't he?
Have you got a way to send it to him, Lewis?
Hang on. Is it the 623 one?
623 509 4578.
Yeah.
4578.
I'll just send it to him. There you go.
4578. 623, sorry, 509 4578. Can you hear us, Roger?
Yeah, hello.
Yeah, you're very distant yourself.
All right, okay. Is that a bit better?
No, you're still very distant.
That's strange.
Have you been waiting a long while, Roger?
No, about 5 minutes. I'm late to the session, Mike.
That's all right. I just didn't want to think I'd left you there a long while. That was all.
No, about 5 minutes.
Trouble is, when you get in full flow, you don't think to look.
Yeah.
EP
Yeah.
is equal to EL over root 3.
Yeah.
Which is 1200 over root 3. And that has given me 692.8.
I'll go with that. In fact, I'll go 693 volts.
Yeah. I went to 4 sig fig because that was what the other one was put in. But
yeah, that's fine. That's fine.
That'll be enough,
yeah. Either answer will be good enough.
Yeah. So obviously it says that the line resistors are 25 ohms for the next part.
Yeah, so this is part A. This is part B. So
for the line or the phase current, sorry, IP.
Yeah.
I've done EP over R. So I've got 692.8 over, or 693 in your case, over 25.
Yeah.
And that's given me 27.71 amps. And I've also made a note as well that in star, the phase current and the line current are the same, so I've just put EP equals IL.
Yeah. In star, IL equals IP.
Yeah.
4 marks for that, for those 2 bits.
Sweet.
All right.
Yep.
Power.
Yeah, so I've done PP, the phase power.
Yeah, for each phase.
Yeah, I've done IP squared times R.
Okay.
I done it differently to that.
Yeah.
Hang on, we'll come back to your method in a minute. Let's see if we get the. So you're done 27.71 squared times
25.
25.
And that's given me 19196 watts.
Yeah. Because I hadn't done it this way. I'm waiting to see if you got the same answer as me. Yeah. So
for PT, the total power, I just done 3 times PP. So obviously 3 times 19196, and that's given me 57588 watts.
57588
watts.
That seems like too much to me.
I think you're putting an extra 7 there.
57.
5.
Yeah.
88.
Yeah, I got a similar answer.
So what did you do, Lewis? Let's do your way as well, because there is more than one way.
I done
Lewis.
S equals IL times EL times square root of 3. So I done 27.71 times 1200 times square root of 3, which gave me 57,594.1.
Just say that again. You done S as what?
No, S equals IL.
Yeah.
Times EL.
Yeah.
Times square root of 3.
Yeah.
And then that gave me.
So that is.
That gave me 50. That's 27.71.
Yeah. Times
1200.
1200.
Times square root
3 equals.
And
you got the same answer.
Yeah,
Sorry?
57594. VA.
And that's, because that's resistive.
Yeah, I put a note of mine saying as load as resistive only, P equals S equals 57.6 kilowatts.
Yeah. Yeah. That's fine. Okay. Just for the record, Mike's solution, none of them are wrong. Both of you have got full marks, right?
Okay.
So doesn't matter. I've gone for each phase. Yeah. P is E phase times I phase. That's 693 times 27.7. I rounded that bit, yeah. I think that's what you've got. Equals 19196 watts. And then P total is 3 times 19196, which is the 57.6 kilowatts. All those methods have the same answer, and all would earn you the obligatory 2 marks for that question. All right?
Thank you, Luke.
Not being asked to do it in any particular way, so it don't matter how you get there, as long as you do. Okay?
Yep.
Then part C, that was part C. Part D, the current flowing in the neutral if one load is changed to 15 ohms. Now here, that'll make a difference which load you change, will make a difference to what the angle is at the end, but won't make a difference to the magnitude of the current in the neutral. Yep.
Yeah.
So, did you do this one, Lewis?
I didn't get that far, no.
No. Okay. Roger, have you done any of these?
Doesn't look like
Can't
he's
hear you. Can't hear you, Roger.
I think he's gone.
I think you might have done. Yeah, he has. He's probably trying to solve his problems. What about you, Ben? Have you had a go at any of these?
Yeah.
Have you had a go at this part?
Yeah.
Part D,
Well,
question 3?
yeah, I've done question 3. Would the 15 ohm one be in the current one?
Well, that's the one I put in my solution.
Yeah, that's what
It's not. It isn't specific, but the only if that was an exam question and you chose a different phase to me, the only thing that would be different is the angle of the current in your neutral. The magnitude would still be the same, so I would recognise that, and you'd still get the right marks for it.
Okay. Yeah, I always thought there was
Okay.
going to be no angle in the neutral, so that's why I done it.
Well, if you put your 15 ohm in the one that's at 0 degrees, then you'll get one angle. If you put it in one of the 220s, either the minus 120 or the plus, you'll get a different angle, but the magnitude of that neutral current will still be the same.
Yeah.
All right, so I would recognise that, and you'll still get full marks, whichever one you put it in.
Well, okay.
Okay, cool.
All right, so what have you done then, Ben?
So IN equals I1 plus I2 plus I3.
Yeah, so IN is I1 plus I2 plus I3. That's Kirchhoff's current law, yeah, so good.
And then I1 equals EP divided by R.
EP over R. We'll be specific in saying that's R1 really, but
R1,
doesn't matter. Yeah.
Which then equal 1,200 divided by square root of 3. Or, yeah, 693.
600 oh yeah, so you're done. It don't matter if you put the 1200 over root 3 or you just use 693 straight, doesn't really make any difference. Yeah.
Divided by 15 ohms.
Yeah.
And that gives you a 46.18 amps.
So yeah.
And
46.2 I got. Angle 0. Yeah. And then what I've done on the end of mine, you got a rectangular as well.
Yeah, 46.2 plus 0J.
Yeah, amps.
I2 is the same process, but when it's divided by 15, it's 25 instead.
Yeah.
Which would then be 27.7. If you want to, I don't know how you rounded it up.
Yes. So what you must have put though is you put 693 angle 120. Yeah.
Yeah. Sorry. Yeah.
Yeah. Over 25. and you got 27.7.
Yep, an angle of
amps, angle 120 degrees, which
rectified
is
minus 13.86 plus 24.
13.9 plus 24J, yeah?
Yep.
Yep, good.
And then I3 would be the same again, but when you get to the polar answer, that would be minus 120.
Yeah, so this would be 693 angle minus 120 degrees in there. Yep.
Yep.
Over 25. So you get 27.7 amps angle minus 120. And this is minus 13.9 minus 24J, isn't it? Yeah.
And then added them together, I got 18.46 plus 0 J amps.
Yeah, so add all the so IN equals 46.2 plus 0J plus minus 13.9 plus 24J plus minus 13.9 minus 24J.
And I got 18.46 plus 0 J amps. And then I converted that to polar, which is, again, 18.46 to the angle of 0.
Yep. Is that what you got, Robbie?
I've done it a slightly different way, but I have got that same answer, but I also put mine in I3, so I've got the same magnitude, but minus 120 in my neutral.
Yeah. Yeah.
But yeah, because what I done with mine was I started off by saying, you know, what is IP new, and then I done it by EP over R new, and then worked that out obviously to be 46.2, and then all I've done was write. We know each phase angle is 120 degrees apart, and then I've gone IN,
again,
and then just wrote
as
them
long
down.
as you get the right answer, the method is immaterial. Yeah.
I didn't go through and work out I2 and 3 again. I just put the angle on the end and said, you know, this,
and that's fine because you're using your knowledge that that angle's going to stay the same. It's not going to change. If you had changed it for a reactive load, that'd be different because if you changed it for an inductive load, then that's going to alter a whole load of different things, isn't it?
Yeah. Yeah.
Yep. I'm not going to give you anything like that anyway. All right.
Cool. Sounds good.
Roger's not back, is he? No. Right. So, question 4. Transformer. Ideal transformer, no less. Have you done this one, Lewis?
No.
You, Warren?
Nope.
You, Ben?
No, that's the only one I can do with question 4.
Okay. Do you want to take us through this one then, Robbie?
Yeah. So just let me try to struggle to read my notes back. Yeah. So I've started off with current I1. I think that gives you the nameplate rating, which I've used as S. So I've done I1 equals S over E1.
Yeah.
Which when you divide 3,200 by 300, you get 10.7 amps.
Yeah, that's what I got.
Question 2, or B, sorry, then asks for I2. So I've taken the formula, which is I2 over I1 is equal to N2, N1 over N2. So when you rearrange that, I2 is then equal to I1 times by N1 over N2.
So you used the formula. You've used the I2.
I2 over I1.
I1
is
equal to
N1
over N2. Therefore, I2 is I1 N1 over N2. Yeah?
Yeah, that's the one. Yep.
Equals?
So on top, I've got 10.7 times 880. And then that's divided by 110, which has given me 85.6 amps.
Yep. Okay, everyone follow that?
Yeah.
That must be the easiest 4 marks on the paper so far.
Yeah, I think, if anything, this question was probably my favourite. That's just you've got one formula to use, and then you sort of jig it about. But yeah,
I'm just giving you a nice little easy few marks here.
Yeah.
For this question.
If you want to do more of that in the exam, that'd be great.
Yeah,
I'm sure it would. C.
Right. Okay. So I've then used the formula E1 over E2 is equal to N1 over N2. And again, here I felt it was best to use N rather than the calculated I's because they're values that were given to you in the thing. So I've rearranged that to be E2 is equal to E1 times by N2 and over N1.
Which is
300 times by 110 over 880, and that gives me 37.5 volts.
Yeah.
Yep. So I've then gone to work out the value of the load resistor for part D.
Yeah. I'll just show you what I've got in my solutions for C. I've got, just checking you got the same answer as me. Yeah, 37.4 I got. All I did was this. E2 is equal to S over I2.
Okay.
3200 over 85.6.
Yeah.
And now I've got 37.4. Volts. Yeah.
Yeah.
What you can remember is that the S is consistent to both windings, the primary and the secondary. Yeah. That's why you get this. If you step voltage down, which is what you're doing in this case, you step current up.
Yeah.
So in this transformer, you're going from 110 volts down to 37 volts. You're going up from 10.7 amps to 85.6 amps.
Yeah.
Because the VA has to stay the same on both sides. You can't get more power out than you put in. You certainly don't really want to get less.
Yeah.
So that 3200 VA applies to both the primary and the secondary.
Yeah.
Again, that don't matter. You've got the right answer. So it doesn't make any difference that you've done it that way. All right? We're just trying to get something across that the S is the same for both sides.
Yeah. Okay.
All right?
Yeah.
D.
Yeah. So for D, I got ZL. I done that as E2 over I2.
Yeah.
Which is 37.5 over 85.6.
85.6.
and that
Equals.
gave me 0.438 ohms.
Yep.
Yep.
And then the power.
I've then done the power is PL equals ZL times I2 squared, which I'll just double check that. Yeah, so for that I got 0.48 times 85.6 squared, and that gave me 3,209 watts. I've called it watts because I'm assuming the load is just resistive.
Yeah, it is resistive, so it will be watts.
Yeah.
Yep. And in this case, as VA as well, because we're ideal, remember, so
Yeah.
we haven't got any of them that tricky stuff to worry about in this question.
Yeah, so the only thing here is obviously that's 9 watts more than the total VA, but I suppose that's probably because of a rounding error somewhere.
Yeah, that will be. All right.
Uh-huh.
Okay.
Yeah.
You certainly can't get more out than you're putting in.
No.
Well spotted. Okay.
Yeah, so that would still be correct, that answer then, and I'll just put under possibly round an error at some point in there.
Yeah.
Okay, cool.
All right. Well, if you're rounded, if you think about it, if you're rounded this current up,
yeah, then that'll
depends
give you
how that's rounded.
Yeah.
And then certainly, if both of them are rounded up, that could be enough to make 2 watts different in 3,200.
Yeah. Okay.
All right.
Yep.
Right. So, longer answer question. Who's had a go at this one?
Not me.
I haven't, to be honest.
You have, Robbie, yeah?
Yep, I have, yeah.
So, first of all,
6.
Hey there, Roger. I thought I heard someone.
No, I was going to say, looking at the people in the group, I don't think he's still here.
No. That's a shame. Right. So, show that the reactive power for the 18.6 kilowatt motor is 21.7 kVAR, and draw a block diagram showing the power flows for the complete system.
Okay,
and then use the diagram to do B to C.
Yeah.
Yeah?
Yeah, so for this one, I've called the 18.6 kilowatt motor, I'll just call that M2. Just the second one in the list. I've drawn a little power triangle for that. And I've put the angle in of 49.5, which I've got by doing, obviously the power factor cos theta is cos, or the cos to the -1 of 0.65. I suppose I went a bit of a roundabout way of doing this one, but I've got 49.5 degrees, so I've put that in the triangle.
Yeah.
And then I've written, obviously, power is 18.6 kilowatts on the bottom there.
Yeah.
I've then used tan theta equals Q over P, which I've rearranged to be Q is equal to P times tan theta.
Q over what did you say? P? Yeah.
So I've rearranged that to get Q equals P times tan theta.
And there you got 18 points.
Yeah, so I've done
18,600.
Yeah, I was just in killer, but yeah, tan 49.5. And then
equals.
I got 21.7 kVAR,
Yep.
Yeah. So yeah, with the block diagram, obviously I've done. Do you want me to, I'll put my camera on so I can show you if you want.
I've got me.
Oh, you've got one of you.
Yeah, you got the answer I got anyway. 18.6. Oh, what, the diagram?
Yeah, I was just gonna say if you can see my camera, I've got a little thing here.
Yeah. What's important is that let me just get a new page. So I'm talking about you guys drawing a diagram where this is the what's the input volts?
450, and then I've put a little 50 hertz in that little top bubble as well.
And then coming off that, you've got your various
So you're playing hangman.
inductive loads. So we got resistive loads, R1, R2, R3, and then you've got some inductive loads, L1, L2, L3. We got an M1.
Mm-hmm.
Your motors should have 2 lines on them.
Yep.
M2, and then you've got 2 capacitors, C1 and C2. The important thing for the diagram, I'm not going to write all them numbers on there, but the important thing is that this is drawing a P, so that the arrow's going out, drawing power, active power, the resistive loads. Yeah.
Mm-hmm.
This is drawing Q, the inductive loads.
Okay, so just with the block diagram then, do we have to draw P and Q? Because all I've done is write each of the values on there.
Right, if you write the values on, the arrow needs to be the right way.
Yeah.
So motors draw P and Q.
Yeah.
So 2 outwards pointing arrows, a power and a Q. Yeah, on your diagrams in the actual exam, you'd write the numbers on.
Yeah. Okay.
I'm just trying to save a bit of time.
Yeah. Okay. Right.
Yeah.
Okay. Yeah.
Power and Q for that, and then the capacitors, the arrows go back the other way.
Yeah.
They are providing Q back to the system by convention. That is, in reality, 1/2 cycle they're providing Q, and the other half they're taking it back.
Yeah.
So we just pick a way, and that's the way somebody's picked. All right.
Okay.
So that's what I would be expecting for that draw, and I'm looking for the arrows to be on the right way, and you've included everything. Yeah.
Okay.
So determine the total active power.
So what I've done for that is I've done PT is equal to R1 plus R2 plus R3.
That's PR1. The power for R1.
Okay, I was going to say because
just a notational thing, yeah.
Okay, so
PR3
and PR3.
PM1.
PM1, yeah, because I called that one M1P, but I suppose that's a better notation that way.
Yeah, doesn't matter as long, but calling it R1, R2, and R3 is a little bit, bit dodgy. Yeah.
Yeah, I see what you mean. I prefer that way. I'll
Put
do
it like this: if you were heading for 100%, you won't get it if you use use R for a power.
Yeah. Okay.
All right.
Yeah.
Yeah. So that is all those powers added together. I don't think I'm going to write them all out. What was your answer?
I got 75.1 kilowatts.
Yeah. The only annoying thing about this app I'm using is the blinking toolbar is down the bottom, and I keep touching it with my wrist.
Yeah.
Doesn't look like that wants to go anywhere.
We'll know. Right. Okay with that, everyone? Yeah. And then total Q.
Yeah. So I've done, going by the new things, PL1,
QL1.
QL1. I'm making a right hash up there with all my notes on top of each other.
QL2. QL3. Minus QC1.
UC1.
Minus QC2.
Yeah.
I'm not going to write them all out. When you sum that all up, you get
65.7 kilovar.
Yeah.
Yeah.
3 marks for that.
Mm-hmm.
ST.
So I have drawn a nice little triangle with P and Q on, and then I've written ST is equal to PT squared plus QT squared. So I've done the
Yeah.
So all that sort of stuff, and I've got 99.8.
S is equal to root PT squared.
Yep.
Plus QT squared.
Yeah, so
75.1 squared. Yep. Plus 65.7 squared. You can use the K's because they're all K, and so your answer will be
in K, yeah.
KVA, yeah.
Yeah, so
you should have 99.8 KVA.
Yep, that's what I've got.
All right. All happy with that?
Yeah.
Yep. And that was part of C. That was actually D is find a power factor.
Oh, is it?
D, power factor.
Oh, yeah. Okay. Yeah, so D, I've done, obviously, power factor is cos theta, which is equal to P over S. So I've just done 75.1 over 99.8.
$75.1 over
99.8.
99.8.
And that has given me 0.75 as my power factor.
Yep. Okay, and the line current?
So the line current, I've done ST Or well, I've called it IT equals ST over E. I'll call it IL because that's the line current, really.
Yeah.
And obviously I've done 99,800 over 450 is equal to 222 amps.
I'll go with that. I've got 222.8 actually, but
Okay.
so yeah, that's fine anyway. You get your 2 marks for that. All right.
Yeah. Okay.
Now E is one of these tricky ones where further capacitance is added to the system to improve the power factor to 0.95. Calculate the reactive power needed to be provided by the extra capacitance, revised apparent power, and the new line current. So you done that one, Robbie?
Yep. So I've called that PF new, which obviously cos theta, which is 0.95 is our new power factor. I've then taken tan theta is equal to, well, I've called it tan theta new is equal to Q new over P.
Tan theta new.
Yep.
So you've got power factor is equal to new is equal to
0.95, which it says in the thing.
Yeah.
And so I've called that, I've basically used tan is equal to Q over P, but I've called it tan theta new.
Yeah.
Is equal to Q new over PT.
Yeah.
And then, so I've rearranged that so that Q new
Therefore, Q new
is equal to PT times tan theta new. And then I've done 75.1.
Yeah.
I've skipped a bit out here. I've done.
You worked out the angle for power factor.
Yeah, I've worked out the angle. Yeah. So yeah, for the angle, I done cos to the -1 of 0.95.
Yeah.
Which gave me 18.2.
$18.2.
Yeah.
So this then becomes 75.1.
Yeah.
Tan.
And 18.2.
18.2 degrees. Yeah.
Yeah.
From which you get.
I then get 24.7 kilovar.
Everybody following that?
Yeah.
Ben? Warren?
Yeah.
Lewis? Yeah?
Yeah, that's fine.
All right.
Yep. So I then worked out how much reactive power would have to be supplied by the capacitor. So I've called that QC.
How you done that then?
And I've done Q old, take away Q new. So that is then 65.7. Take away 24.7 is equal to 41 kilovar.
Yeah.
I've then gone on to work out what the new apparent power is. So I've called that SU. And for that, I've done the square root of PT squared plus Q new squared, which is, obviously root of 75.1 squared plus 24.7 squared. And that has given me 79.1 kVA.
Yep. Everybody follow that for a couple of marks?
Yeah, fine.
You'll see where the Q new comes from in terms of, or where the Q being supplied by the capacitor comes from. You're taking the original, the new Q away from the old Q. Yeah. So originally we had a Q up quite high, but now we're coming in with a lower Q, reducing the angle. And so this bit here being supplied by the capacitor is the difference between the old Q and the new Q. Yep.
Yup.
All right. Just give me a minute, guys. My battery's getting low on my iPad. I just need to plug it in. Right. And the next part is?
Yeah, so that is the new line current. So I've done I new.
Okay.
Is equal to S new over E.
I new is equal to S new over E.
Yep. So that is 79,100.
79,100
over 450. Which gives us 176 amps.
Yep. Okay. Now, that isn't all the marks there. If you total them up, okay, because in the actual exam, I might put in there a further 6 marks will typically be awarded by you drawing on your knowledge of power supply systems for the benefit to talk about or answer about the benefits of power factor correction and the implications of having poor power factor. Right now, it's quite obvious. I'm not going to give those answers away in a practice question. Right?
Yeah.
So, you know, you need to make sure you've got your knowledge of power factor correction and why we might use it for the remaining 6 marks for that question. Okay.
Yeah. Luke, just on those word questions, I noticed we've had a few word-based ones at the end of some of our tutorial questions, things like, you know, what are the assumptions for like a ideal transformer and things like that. If we were to just do a bit of revision back through our past lecture notes, what sort of worded topics come up? Is it things like power factor correction, ideal transformers, real transformer? You know what?
Yeah, that type of thing.
Okay.
Yeah. All right.
Yep.
So that's just a way of me determining that that's not just about doing calculations. That's about understanding the systems as well.
Yeah, of course.
Yep.
Yeah.
All right.
Yep.
And why things are the way they are. All right.
Yeah.
Okay, so that is them questions done and dusted and had a look at. You're all happy with that? Yeah.
Yeah. Are you able to go back to slide 11 at all?
Of course, I can go back to slide 11. There's that Have I got the right one?
Yeah, I just missed one of the notes, that was all. Yeah, I just missed out that triangle.
There you go.
Thank you.
That should be a right angle triangle there, Warren. That's not very much like a right angle triangle, but that's what it's meant to be. So there's meant to be a right angle in there. Okay?
Yep.
That's like the leaning triangle of pizza. All right, so what we'll do now then is move on to the full practice exam paper. Yep.
Okie doke. Just a quick
Have you all
question.
got that? Do you want me to put up on the screen, or
I've got it printed off here, yeah.
what about the others? I was just going to have a little bit of a talk through the paper and just the general guidance and the questions. Just look through it before we start on it. Yeah.
Yep.
And then I was going to leave you to work on a question or two and work on it that way, and then we'll finish it off next week.
Okay.
All right. So I'll just share the practice paper with you, if I can.
Yeah. So just before we talk about this, I just had a quick question. So what we've had before with previous exams is, obviously, I normally just use the tutorial questions to revise, but I did notice some things like unbalanced three-phase and some things are only in the actual lesson booklet. The questions we've done in there. So I was just wondering if we could get a quick overview of what subject areas we need to revise to be in the exam, because I don't know, things like motors, is there going to be any, like, when you talk about like the synchronous speeds, is there any of that in there, or?
No, because that part of the learning outcomes was covered by the assignment.
The assignment, yeah.
Yeah. So what's covered in the examination are the calcs we've done in class.
Okay.
Yeah. We'd never done any real major calculations around motors other than poles and synchronous speed, did we?
Yeah, no. So things like the open and close transformer, is that going to be in there potentially?
Yes, that potentially. The transformer model. I think have you had a look at the paper, the practice paper?
I haven't yet. No.
Mm-hmm. We're now going to look at it, Robbie.
Okay. All right. I'll hold the question till the end then.
Yeah. I mean, obviously, I can't fit every type of question in one paper.
No.
But you'll get a flavour of what could be included. Yeah.
Yeah.
Find the damn thing. Oh, here we go. Right, can you see that?
Yep.
Yep.
Okay, so practice paper, 2 hours, all right? 3-phase power distribution systems. So we've got 4 questions in section A. They're worth 10 marks each, and you should attempt them all. Mm-hmm. Yeah. And then section B contains 3 questions, each worth 30 marks. You should attempt 2 questions in this section. All right. You've got a data sheet at the back of the booklet you will have in the real exam. I don't think there is one in this. While you're working on a question, I'll just take a look at that. We'll see what's in it. I'll share it with you. All right. So, question 1, single phase motor, parent power, active power, reactive power, etc. We've got a question about using some complex arithmetic to solve a power question. We've certainly done an example like that in class.
Yeah, don't like that.
3 different loads connected to a 3-phase neutral. Yeah.
Mm-hmm.
Calculate the current flowing in each phase and calculate the current flowing in the neutral conductor. You've got, which we already said today was a relatively easy, but you've got an ideal transformer question.
Mm-hmm.
That's got a transfer and impedance down the bottom, but that shouldn't hold you too many. So that's section A. So there's 40 marks there. So if you can nail that, you're nearly passed. If you can get good marks in all those 4 questions. If you get 100% in all them, you have passed. Question 5. Watt meter and a var meter connected to a line. Yeah. Carry out the following analysis. So this is one that's kind of got a bit of a power and reactive, real power and power factor correction issues. All right. Again, the 6 marks, I haven't been very specific about what I would ask there, and there is no solution for part A in the solutions. Okay. Question 6. Resistive loads to 3-phase star connected. Yeah. I think, and then halfway through, you've got same load connected to star. Yeah, so you start off in delta and you go to star. And then a case where it becomes unbalanced by connecting a different resistant load to one phase. So it's like one we had a look at tonight, but a bit longer overall. Question is, and then question 7 is transformer model question. So you've got transfer and impedances and various bits and pieces there. I must say, over the years, I don't think the transformer has been a very popular question for people to answer.
No.
But there's nothing really to get too kind of hung up about over it. They're all fairly even in difficulty, in my opinion. You know, they're fairly well tested as taking the right amount of time to do, and you know, we don't have massive problems with people not passing this exam, so I must be doing something right. Okay.
Yeah, I think
so.
From the initial look over, I think my least favourite areas is probably 7. I don't mind the ideal transformers, but the real ones sort of mess me up a bit. And then probably something like question 2, I tend to mix up a lot on there, but we'll go through, see what happens. And I've got plenty of time.
If you wanna start having a go at question 1, and then if I were you, I'd kind of work together a little bit. So yeah, you want to have a go at it yourself, but help each other, and then and ask me if you're really stuck.
Okay.
All right. And then we'll carry it on next week from wherever we get to this week.
Okay.
How are we carrying out the exam? Because with Adrian, we're using Brightspace.
Yeah, we're gonna use Brightspace, Ben. In fact, in a minute, I'm gonna just set up a test one because I've been on it myself, but I haven't seen it with students connected, and so I just wanted to make sure I can set it up right.
Right. Okay.
So I'm going to ask you right near the end tonight if you can just connect to it and what have you. All right?
Yeah, that's fine.
Yeah, okay.
So give us a shout if you need help, all right?
Okay. Just notice this is still recording, Mike.
Is it?
Yeah, well, there's a little recording thing up in the corner. I don't know if